Now let us understand about the beam divergence loss, because the beam is diverging and then we have a limited area where the beam is falling. Rest of the optical intensity is beyond that area and it is a loss. So let us try to understand this beam divergence loss. So beam divergence loss, let us assume that there is a transmitter here and this is the transmit optics here. So this will become something like this. So my beam area is something like this and my detector area is something like this. So this is the receive beam. This is the receive beam. And this is the detector. And let this distance be R. And this transmit aperture is say dt. This transmit aperture is dt. And here this receive aperture is dr. This distance, this area is dr. Basically between this and this. So this is your dr. And let me draw a middle line as well here. So let us see the spread due to diffraction and then what is the power collected in the receiver. So PR is given, I'm assuming other components are equivalent to 1, the neta T or the pointing loss or the receiver optics or the filter. So let me use a simpler formula where I have the transmitter gain, I have the transmit power, the receiver gain and the free space loss. So this is a receipt power. And we know the free space loss is given by lambda by 4 pi r square. The GT, as we had discussed, is given by 4 dt divided by lambda whole square. And GR is given by pi dr by lambda whole square. So if I put the values of GT, GR and LP here, then what I get is PR is equal to PT, transmit power, into dt over dr divided by lambda r whole square. And if I convert this dt into area, corresponding area, using area is equal to pi r square or pi dt by 2, we have assume. So in terms of area, this is 4 by pi whole square into AT AR divided by lambda square r square. So the geometric loss, which is actually the ratio of this taken in, because I'm calculating this in dB, so this will be given by this minus 10. This, because of the square comes here, 2 log 4 by pi plus log AT AR lambda square r square. So this is geometric loss I will face. So source with the narrow beam divergence are required if I want to have this loss low. So I required a source with narrow beam. Source that will change my AR. Source with narrow beam is required to reduce this geometric loss, which is again a issue of alignment issue will come. So just to give an idea, for example, if I have theta divergence as 2 to, for example, 10 milliradian, this is theta divergence. It will give me a beam spread on the receiver, which is 2 meter to 10 meters. This is beam spread. So the beam spread is quite high. So I may not be requiring any tracking mechanism. So no tracking may be required. If I make low theta divergence because I want to make this geometric loss low, then if I select, for example, this kind of laser which has 0.05 to say 1 milliradian divergence, it will give me 5 centimeter to 1 meter. And this is quite small. 5 centimeters is quite small. I need strict alignment. So I need some tracking mechanism here, which makes the system complex. Tracking mechanism. Right? So if your beam width is low, you require strict alignment. And for making that strict alignment, you need to have some tracking mechanism in the system, built into the system. So again, there is a pros and cons of having low divergence angle. So how do you get rid of this problem? So sometimes one can use a beam expander. So beam expander actually is a two-lens system. So you have, for example, this is a source, and it is emitting like this. And then you have a first lens here. It converges the light here. And then you have another lens which will, collimate the beam. So this is a use of beam expander. It's a two-lens system. And if I calculate the PR ratio of PR and PT, so PR actually will be proportional to dr square. This is dr here. And PT will be dt, that is, this is dt plus divergence angle into r whole square. And if I calculate the geometric loss, it will give me minus 20 log dr divided by dt plus theta div r. So here you see, as compared to earlier, the geometric loss is less. And because the geometric loss is less, you get more power at the receiver. So there is improvement in the performance because you have got more power because of this arrangement using beam expander. So this is how one can sort of handle the beam divergence loss using beam expander or a two-lens system. The next loss is actually a pointing loss, which is very important. Again, it is related to the alignment. So what happens actually, suppose your detector area is this much. This is your detector area. This is, this is my detector area. And say it is radius A. Now the beam which is arriving at the receiver, if it covers this whole area, then this detector gets the whole light. So there is no pointing loss. But if that does not happen, because this pointing loss may happen because of, the sway in the building, or transmitter and receiver are, because of the wind, they are misaligned, or there may be some mild earthquake. So because of all these things, this received beam which you receive will be something like this. So this is your detector area with A, and your received beam will be something maybe like this. So only part of the received beam is available to the detector. And this is changing with time. I mean, this is not constant. This is changing with time because of the misalignment happening. So what basically you do, you model this, the changes happening in the X direction and in the Y direction as two independent, processes. And if I draw a vector R, which is from this origin to say middle of this beam, the recede, this is recede beam, and this is a R vector. This R vector is actually changing because your beam, because of the pointing, is changing with time. So this R vector actually follows a Rayleigh distribution. And with variance sigma square. So this has been seen, empirically studied, experimentally seen that this R vector follows a Rayleigh distribution with variance sigma square. So in order to quantify this pointing loss, I define a factor called G, which is, this is the equivalent beam width of the received beam at the receiver divided by the 2 sigma s, which this is standard deviation which has come after I have assumed that this R follows the Rayleigh distribution with variance. This is variance sigma square. So this G can have value from 0 to infinity. So if your sigma s, there is no variance, is 0, so this G is infinity, that means there is no pointing loss. G is infinity for this case. But that is not the case. So G has some finite value, can go up to 5, 6, 7, 8 or whatever. So which is actually tells you the amount of pointing loss you have in the system. So this is about the pointing loss, and this loss can be written in this form, which is exponential minus 8 theta square jitter divided by theta squared divergence. This is a divergence angle at the transmitter, and this is the angle this is making, this R vector is making, and this angle is changing because, as I told you, it follows the Rayleigh distribution, and because of different conditions, this alignment is changing and this beam width is changing, and the R, this vector, makes an angle theta which is changing, and I'm calling that angle as theta jitter. So you can get some approximate value of pointing loss by using this expression, exponential minus 8 theta jitter square divided by the divergence angle square. So this is how you can get the pointing loss. Okay, now we will start a link design for a free space optics, and we will take 2 examples. One is for a terrestrial link, and other example we will take for a space link. So through these examples, we will understand what kind of transmitter is required, what kind of receiver is required, what is the divergence required, and what are the different receive aperture and transmit aperture or transmitter gain or receiver gain are required for designing these 2 links. So before we understand those numerical examples, let us try to understand using this slide what are the things which are involved in link design. So as you know, the link design consists of one transmitter, then there is atmosphere, and atmosphere will have propagation loss and also loss because of the atmospheric conditions or because of the environment. And then there is a receiver part which also has some amount of loss. So in this graph, in this slide, on y-axis is optical transmitter in dBm, and on y-axis, on x-axis is the actual distance. You can say this is r. So as you see here, the transmit power is 10 dBm. And because in the transmitter there are some lens arrangement, so there will be some loss because of that lens arrangement. So this loss is depicted by ATX. That is a loss because of the transmitter, which could be few dB, 1 or 2 dBs. So that loss is considered here. And then as light travels in the open outdoor environment, there will be a propagation loss, which is written here, and the loss falls in this fashion. And then, and as you reach some distance, suppose there is a clear weather, there are no environmental, effects. So in clear weather, the loss which happens in clear weather is quite less. So this will follow this dotted line. And then because of the receiver, there will be some loss because of the receiver optics. So you get something here. So you point after 4 kilometers, you get something like this. And if you see this power, it falls in this range, which I have defined as PR min and PR max. So this is the detector range. PR min is the sensitivity of the detector, the minimum power it can sense for giving some particular performance. And PR max is the maximum power it can have, because if you give power more than that, it gets saturated. You don't get any corresponding output if the power exceeds PR max. So there is a window defined for a good receiver operation, which is between PR minimum and PR max. So as we notice here, if it is clear weather, then I'm able to cover a distance of 4 kilometers, and my receive power is somewhere here, which lies in this range. But on the other hand, if this is not a clear weather, and the weather has fog, then the fog will introduce attenuation, and that attenuation is quite high, that we had discussed earlier. Depending upon the nature of the fog, the attenuation per kilometer changes. So this value changes, and if you notice here, this is the receive power after you have encountered the fog and the receiver attenuation. What you get is this point, which is actually falling below this range of detectors. So it may not meet your performance. The link may not survive up to 4 kilometers. The maximum it can survive will be, say, somewhere here, where the light falls within this region. So about 2.5 kilometers under foggy conditions. So based on this understanding, let us see the different values of system parameters for a terrestrial link and a space link. So this is an example of a terrestrial link where I have considered one wavelength, which is 1550 nanometers. This is same as used in optical fiber communication system. The distance which I am referring is 1 kilometer, and I am interested in transmitting 1 gigabits per second of information. The received diameter I have used is 100 mm dr, and the divergence angle theta t, or you can write theta divergence, is 1 milliradian. So the transmitter antenna gain can be calculated using 16 by theta t whole square, theta divergence whole square, because we had seen that transmitter gain is 4 dt over lambda whole square, and theta divergence we also know is approximately dt by lambda. So putting in this value of dt here, you get expression this is 16 divided by theta divergence whole square. So this gt is this, and if I convert this into dB, it is about 72 dB. The space loss, because of distance r is 1 kilometer, lambda is 1550, one can calculate the space loss, which is equivalent to minus 198.18 dB. This is minus because this is a loss. And this is plus because there's a gain. The receive antenna gain, which is given by pi dr divided by lambda whole square, and dr is some 100 mm here, lambda is known. So based on this, you get some gain, which is 106, approximately 106 dB. So effectively, there's a loss here, but there's a gain because of the transmitter antenna, because there's a receiver. So effective gain, still there's effective loss, which is minus 20 dB, because the loss because of the space is high. Now, if I take a transmitter output power of 1.26 milliwatt, which is actually 1 dBm, and I assume that there's an optical loss of minus 5 dB as a transmitter, in terms of dBm, minus 4 dBm, the total loss will become, because earlier it was minus 20 in the last slide, then this gets added up, and what you get is minus 24.003 dBm. Then there is loss in the clear visibility and without pointing loss. I'm assuming that there is a clear weather and there is no pointing loss. So because of that, a factor of minus 2 dB, which makes it minus 26 dBm. And then receive optical loss at the receiver, where you have the receive aperture or some lens arrangement. There's a loss of minus 5, so that makes it minus 31. And minimum power I require for 1 gigabits at a distance of 1 kilometer and at the bit at a rate of minus 9 is minus 36 dBm. And the loss is actually minus 31. Still, I'm left with some 4.997 or equivalent to 5 dB, which I call as a link margin. And this link margin is actually takes care of aging of the components, or if some misalignment sometimes happens, or some optical transmitter at some with time the power output decreases. So you also build some sort of link margin in the system, which takes care of future aberrations or future issues which might come because of different reasons. So this particular example, if you have a transmit power of 1 dBm and with all these parameters, this system will work for a distance of 1 kilometer for 1 gigabits per second and give you a 5 dB margin. So this is an example of a terrestrial link. Now let us see a link analysis example of a satellite to ground laser communication. And this distance is going to be huge. So right now I have considered as wavelength as 0.635 micrometer. Range, this distance is quite high of this order. We are talking about satellite to ground. And I'm also talking about high data rate, that is 3 gigabits per second. The receiver diameter, let us assume, is 1.4 meter. The divergence angle is actually in milliradians, or you can see 2.07 into 10 to the minus 4 radians. So it is very, very small. Otherwise, you cannot cover a long distance. So, and transmitter antenna gain, as discussed in the last formula, you get 85.72 dB, and the optical loss at the transmitter is minus 10. Space loss because of the distance, this is going to be huge because the distance is quite high. You see the distance here. Distance is here. So this is about minus 259 dB. And receiver antenna gain with these, this is pi dr, this is dr divided by lambda whole square, gives a gain of 136. So you got a gain, transmit gain here, you got receiver gain here, but there's a huge loss here because of this and because of this. So optical loss also, there will be some at the receiver. And the system loss, basically, if you add up all these things, will be about 57 dB. I have kept some turbulence margin of 11 dB. This turbulence we will discuss in detail because there will be issues because of the atmospheric turbulence. So this I have kept at minus 11.30 because such a long distance you will encounter turbulence. clean air transmission loss is quite less because we are talking about space to ground, and good part of the distance will be actually clean air where the loss will be very low. So the total link loss becomes minus 70 dB, and I want to keep a link margin of 6 dB. I mean, this is generally kept, for to take care of any issues which might come with time. So the total design loss is minus 76.46. And at 3 gigabits per second, I require at least this much power at the receiver. Only then I'll be able to decode. There is some PR minimum required at the receiver for 3 gigabits per second and meeting 10 to the minus 9. And that power is actually equal to minus 17.29. So you can back calculate what is a laser power required at the transmitter, because you know the system loss, you know what power you require at the receiver, and then doing this simple mathematics, you can calculate what is the laser power required at 3 gigabits per second, which comes out to be 4.414 watts. And so this is the requirement. So you require a laser power of 4.14 and very, very low theta divergence, very, very narrow beam in order to cover a distance of from satellite to ground. So this is some of the typical values which one can use for calculating or for identifying different components for a space link. So with this, we close this discussion on free space optics. We discussed about different, what are the issues with a optical wireless channel in outdoor. We discussed about, different loss and different transmitter gain and receiver gain. And we also discussed about the pointing loss. And we derived a range equation for calculating what kind of power, transmit power is required, what kind of receive power is required. And this we had discussed using two examples. One example of range equation for a terrestrial link, and the other example for a longer link, which was between satellite and ground station. So far we have discussed about the absorption part and the scattering part, but we have not discussed about the turbulence part. So in the next class, we are going to discuss the atmospheric turbulence and how can we model atmospheric turbulence, and what are the ways of mitigating atmospheric turbulence, and what effects it has on the link design, that we will discuss in the next class. Thank you.